Hello everyone, here is Yuanhui, and here I will go over the homework 10, question number 2. In question number 2, it's asking me to go over each follow of the stochastic process. And let's see. The first one is a Weizsäcker stationary process. And in the Weizsäcker stationary process, if its mean is constant and autocorrelation is function of time difference, so which means it's WSS. And so we can see from the we can see some like definition of the Weizsäcker stationary process. First one is WSS only use mean and autocorrelation. And second, it's based on mean and autocorrelation function. People can do state estimation, parameter estimation, and prediction in the mean squares. And then the autocorrelation function RT1, T2 for T1 equals to T2, which is RT1, T1, it's the average power of the signal at T1. The next is when input is WSS process, the output of stable LTI system is also WSS. Next, XT is SSS, and expect value of x power of 2t exists, which means xt is WSS. And second one is independence increment process. It means xt1 minus xt2 and xt3 minus xt4 non-overlapping overlapping interval at independence. So it says Poisson process, random walk, and Wiener process one independence increment process. And second is independence increment implies and correlation increments. The third one is Markov process. If the past has no influence on the future, when the present is now as xt is alpha. So we can see Poisson process, Poisson impulse, semi-random telegraph, random walk, and Wiener process are Markov process. And for any n and T1 larger than T2, blah blah to Tn, so we have probability of xt1 smaller and equals to x1, which is condition of the xt1 equals to xt2, xt3 equals to xt3, blah blah, until xtn equals to xtn, which is equal to xt1 smaller and equal to xt1 of the condition of xt2 equals to lambda. Then in the third part we can say a Markov process is statistically determined if one knows its second order distribution function. So the density function of x1, x2, t1, t2. And for the fourth, it's normal process, which also means Gansen. It says a process xt. A process xt is said to be normal if the random variable xt1, xt2, blah blah until xtn are jointly normal for any t1, t2 until tn. That is, that's a function of xt1, x1, x2, blah blah until xn, and t1, t2 until tn is equals to this function. So there we can get the function of x, and so the c equals to expect value of x from above. We can see the statistic of normal processes complexity determined in the term of its mean. So N1, NT, and autocorrelation RT1 and RT2, or auto means CT1 and CT2. And we classify normal process as a property of stochastic process. So the next one is strict stationary process. We see that a real stochastic process of xt is stationary in strict sense if its statistic is not affected by shift on the time axis. So we can see that's a function of x and t equals to that's a function of x1, x2, blah blah until xn, and t1 plus sigma, t2 plus sigma, blah blah until tn plus sigma. For any n, any t1, t2 until tn and sigma. And second is any sequence of IID random variable is ASS. And next one is xt is SSS2. That's a function of x and t, which is equal to this function of x. xt is SSS to expect value of xt, and which is constant, and if the increment exists. And xt is SSS, so we can say that function x1, x2, t1, t2 equals to that's a function of x1, x2 and t1 minus t2. And since x1, xt is SSS, which means the r t1, t2. And next one is white noise for Werner process. WT. If we wish to discuss this derived Vt equals to derived mu t, we have expect value of Vt equals to derived t expect value of Wt, which is 0, and Rv22 equals alpha times eta t1 minus t2. A stochastic process Vt is said to be a white noise if expect value Vt equals to 0 and Rv1 t2 equals to q t1 eta t1 minus t2. So for the silent, it's a mean ergodic process. Stochastic process xt is said to be a mean ergodic process if limit of t to infinity times 1, which is 1 over 2t, and from t to t, and dt, which is equal to expect value of xt in mean sequences. And we can say in mean sequences it's kind of consistency. And the last one is martingales. Martingales as stochastic process xt is said to be martingale if expect value of xt of condition x as equal to s is equal to x, where s smaller and equal to t. So we can say the condition mean squares the condition. The conditional mean squares the condition. This is true for random walk and Wiener process. That's all for question number 2. Thank you for listening.